Hello, this is Dr. Marina Wal Sabrajmail from the Lebanese University. In this second chapter, we are going to talk about the fundamentals of PLC programming. So we are going to talk about ladder logic. We are not going to discuss the other software programs because ladder logic is the basic program that we use in PLC programming. We are going to describe some ladder diagram symbols, the basic contacts and programming. This is normally open, normally closed, series parallel, and the start-stop circuit. We're going to end with the description of the PLC scanning and scan time and talk about its importance in how you are going to program. You have to take it into consideration. So as we said, ladder logic was there to replace the relay. And this is the description of the relay, the basic relay. So in a relay, we have a coil. We have, this is a normally open contact, and this one is a normally closed contact. And this example, in this image, we have a load connected to the normally open contact. So if everything is normal, so the coil is not energized, the load is off. When the coil is energized, there is a force of attraction due to the magnetic circuit inside, and this force of attraction will go and take this metallic edge and take it from the normally closed to the normally open, and the normally open becomes a closed circuit, so the load will be energized, and if I had any circuit on the normally closed, it will turn off. So the normally closed is what we call inverted logic with respect to the normally open, which is the regular logic. So in ladder logic, we are going to use this scheme, the coil, the normally open contact, and the normally closed contact, and we're going to write them in a program which looks more like lines of code that we call rungs. So this is the coil, the output, and this is a normally open contact. So we're going to put the contacts as inputs and the coils as outputs. So this is how we are going to represent a normally open contact and a normally closed contact. This is a very basic circuit just to see how the PLC is wired and how the program is written. So in here, this is the ladder program. We have the first rung. It's just one rung, extremely simple program. This is the input, which is a contact. In this case, the contact is not the output of a relay. It is the input. And the output is a coil that is going directly to the output module. We have a circuit which has a one input with a push button, and a program that says if the input is on, let the output be on. Of course, a program like this does not require a PLC. This is just for the example. So once the output is energized, this means this button in here has energy on it, and the output is connected to it, is going to have current passing through. And here we have the bell that is directly connected. Usually we have an external relay which itself is going to give energy to any other circuit, so that we don't absorb the energy of our outputs from within the PLC, to protect the PLC. Example of a normally open switch, a practical example where in here we don't have a PLC. If the door opens, I have this button that closes the circuit. This is a normally open button, and the circuit puts an alarm on. So once the door opens, the alarm turns on. This is in case you don't want anybody to open your doors. Normally closed, as I just said, is the opposite logic. It's always closed except when I want it to open. So we have in here an example. We have a robot that's functioning inside, maybe controlled by a PLC in here. And the current of the PLC is connected to a wire. And as you see, the wire is going all around the room. So if I have many different gates, they are going to be connected in here with normally closed switches, and whenever any of these gates is going to open, the circuit which is normally closed, giving current to the PLC to function, is going to open. And once it opens, the PLC of course turns off and the robot stays still so that it doesn't hurt anybody that could come in for maintenance or checkup. So this is a case where I can possibly put many different doors, gates in here, and they can all function at the same time. So usually, normally closed switches are used for security reasons, where normally open switches are used for normal functioning of the circuit. This is a normally closed contact connected to an output, in which we call it in here an alarm. The contact is open because it has current on it. Once the current, the input, is off, the normally closed contact will close and the alarm would run on. How to connect multiple contacts together. So for example, in here I have an example where I want a hand drill to drill items, and I want to be sure that the worker has his two hands off the part underneath the drill so that he doesn't hurt himself. So I put two switches in here for left hand and right hand, and the part sensor. So I want the hand switch 1 to be on and the hand switch 2 to be on and the part in its place, so part sensor, to be on before I can turn on the drill motor. Therefore I have to put them in series so that any of them not in place would turn the circuit off. The current will not pass. Therefore, when I talk about the AND logic in logic circuits, implementation in a ladder diagram is in series. Of course, you can deduce that if I want an OR logic, they have to be in parallel. So an example in here is either the front door is ringing or the rear door is ringing. So as applied, the doorbell will ring. Start-stop circuit is a circuit that starts with a start push button. When you remove your hand, it will keep on functioning and stops whenever you press another button. So complementary to the switch logic, it starts in here. I have a push button which is normally open. I have a stop push button which is normally closed. So if it is not energized with a normally open contact in here, the current is always passing. So this one has current always passing. The start has a normally open, so the current does not pass to Y1, the output. Once I energize the start one, I close the start button, current is going to pass through this one, and this one is closed, so it's going to pass. Y1 is going to be energized. What I have in here is a contact connected to the Y1 coil. So whenever Y1 is energized, the contact in here closes and allows current to pass. Therefore, this ensures that the current is passing and energizing Y1. If I remove my hand from the start push button, this one stops the current, cuts the current, but the current is always passing through here. The only way to stop it from going to Y1, therefore turning it off, is to cut the circuit beyond the parallel lines. So this is why the stop push button is put outside the parallel to Y1. So the circuit turns off and I can only restart it with the start button where the stop button is not pressed. So if you press start and stop immediately together, the machine will not start. The question below is, how would I change this circuit so that it functions if the stop button is normally open as well? Of course, you can deduce that you have to invert it in here. So when I invert a logic, I either invert it with the button or within the program. I don't do that twice because inversion is like any inversion logic, like in logic circuits. If you invert it twice, you eliminate it. So if the stop button is normally closed, I use a normally open circuit in here. If the stop button is normally open, I use a normally closed contact in here. The easiest way is to consider all the push buttons normally open, analyze your circuit as you would consider them all normally open and just invert the states whenever you have normally closed push buttons. Okay. So output latch instruction, of course, a start-stop circuit would be easier if I would start the circuit with an output latch. This is going to, instead of the output being on only when current is coming to it, it's on when it just gets a glitch of current, and is going to be off with an unlatch instruction. So instead of having a coil which is energized when it receives current, I have the start-stop logic within the latch unlatch outputs, and these are connected directly to the output. So they have two ways to control the output, either by coil or by latch and unlatch instructions. Another instruction that's useful in logic programming is jump to a label or jump to a subroutine. Subroutines are programmed within the PLC. We can permit ourselves to put several sub-programs with a selector switch selecting between them. This is the only way to put more than one program onto a PLC. Jump to label is in order to skip useless instructions whenever we do not need them, and of course use them only when we need them. We have many other special contacts. Not all of them are available in all the PLCs. We are discussing some of them in later chapters, and of course whenever you want to work with a PLC, you have to go and read the manuals of the PLC and check what contacts they have and what functions they have, because many of them have many different possibilities, going up to analog PID control and many other flow controls. When you talk about the scan time and the scanning of the PLC program, whenever a PLC wants to run through a program, a PLC runs continuously the program. It doesn't run the program once and stops. It continuously runs the program. At every time it runs the program, it reads the inputs, updates the input image table, then it evaluates the whole program. After it evaluates the whole program, at every time it gets an output, it saves it in the output image table. And only after it finishes the whole ladder program, it updates the output to the output module. So we have between 20 and 50 milliseconds as a scan time for a PLC program. This is large if you want to talk about controls by microcontrollers, but it is fast enough for most industrial procedures. Therefore, it is good for most applications. Whenever the scan time is slow, we usually implement a C-based program for the very fast functions that we use in the industries. So this is an image that is showing us the PLC program, whatever we have, and then once it finishes evaluating, it updates the outputs, updates the inputs into the input image table, and goes back to evaluating the program. It only stops when you turn it off. This is the end of chapter 2. Thank you.